Welcome everyone, and thank you for joining me. Today I'd like to navigate the evolving situation with capsule suspension formulations in light of the new constraints around microplastics. Let's begin with the fundamentals. A capsule suspension is essentially a water-based dispersion of tiny polymer microcapsules. Think of each capsule as containing a core with an active ingredient dissolved in an organic phase, all surrounded by a protective polymer shell. Now, this is not just packaging, it's engineered protection. The benefits are compelling. We get long-term storage stability in water-based concentrates, reduced operator exposure to harsh chemicals, and the ability to co-formulate ingredients that would normally be incompatible. Polyurea capsule suspension is the market benchmark case. Let's see one example of polymer shells, the polyurea shell, which is currently the most widely used type in industry. Polyurea shells form through interfacial polymerization. Diisocyanates from inside the droplet mean diamines from the water phase, creating an instant reaction that forms urea bonds simultaneously across every droplet surface. We have three control levers. Monomer functionality, linear gives fast release, trifunctional gives stronger shells but slower release. Temperature and time, higher gives better conversion. NCO to NH ratio, slight amine excess prevents brittle shells. The main chemistry is straightforward. Isocyanate plus amine equals urea bonds. That's your shell. But watch out. Isocyanate plus water makes carbon dioxide gas, swelling the capsules and creating popcorn defects that weaken the shell. The result? Shells that are 80 to 400 nanometers thick, 1000 times thinner than hair, protecting content for 2-3 years. Process outline for polyureas. Now let's look at the actual process for making polyurea capsules and the critical control points. The process follows a logical sequence. Build your aqueous phase with dispersants and amines at pH 5 to 6.5. Prepare the organic phase with active plus isocyanates, then emulsification. And this is crucial. This step sets your capsule size destiny with target D90 around 5 to 10 microns. The magic happens during polymerization, where you manage that critical NCO to NH ratio of 0.9 to 1.9. Finally, post-cure and quench with monoamines like ethanolamine to consume residual NCO groups. Then add finishing touches: antifreeze, rheology modifiers, biocides. Key control points throughout. Monitor pH constantly. Track particle size distribution during emulsification. And most critically, during polymerization, control NCO to NH ratio and temperature ramp while measuring percent-free active ingredient outside the capsules to ensure proper encapsulation efficiency. Now let's talk about capsule size distribution and how to achieve your targets. Remember this key principle. Capsule size mirrors your emulsion droplet size before polymerization. Once those shells form, there is no going back. Your rotor starter conditions, surfactant system, and phase properties all determine your final size distribution. Preventing droplet inflation by carbon dioxide release is crucial. This happens with NCO excess or too fast reaction at high temperatures. For foliar CS, we target D50 in the low single micron range and D90 under 10 microns. Shell thickness control in CS formulation. Relationship to capsule size. Shell thickness control is trickier than many realize. Here's the key relationship. Under typical dosing approaches, shell thickness scales linearly with capsule radius. Smaller capsules with the same monomer recipe gives you thinner walls, higher permeability, and more free AI. It's a geometric reality we have to work with. For foliar applications, we are typically looking at 80 to 200 nanometers. Thin, fast designs might run 40 to 80 nanometers, while rugged, slow permeation designs can go 200-400 nanometers. Encapsulation metrics, percent-free AI, and solid stress release. We use two principal metrics to assess encapsulation quality and capsule integrity. Percent-free AI, baseline metric. The principle here is to separately detect AI that's outside the capsules and divide by the total AI content in the formulation. We centrifuge to separate encapsulated from non-encapsulated material, then measure the free portion. 1 to 3% at baseline is excellent. Less than 5% is acceptable. More than 5% needs investigation. Solvent stress release test. This tests wall robustness by exposing capsules to miscible solvents like IPA and acetone water. We measure AI released from stressed capsule walls. It's for evaluation of wall integrity, not predicting release kinetics. Together, free AI shows baseline encapsulation quality, while solvent stress shows shell robustness. They help identify undercured walls, porosity issues, and storage leakage risks. Mechanisms of AI release from CS formulations. In the field, release is governed by multiple mechanisms working simultaneously. Water plasticizes the shell, enabling diffusion. Osmotic pressure from initial dilution drives fast early release. Drying concentrates salts and surfactants, altering wall permeability and causing mechanical shell failure. Then reventing events, dew, irrigation, rain, each causing wall swelling and rupture, potentially triggering more release. Add chemical degradation from hydrolysis and photolysis to complete the picture. Environmental impacts on AI release. The field environment creates unpredictable factors that dramatically affect release. Water cycles, dew to dry to rain, each triggers different mechanisms. Temperature swings of 20 to 30 degrees daily affect diffusion rates. UV exposure embrittles shells, leading to sudden burst release. Chemical variability, pH, hard water, adjuvants, all destabilize shells. To summarize, multiple mechanisms operate simultaneously, and each environmental change can shift which mechanism dominates the release pattern. AI release, lab insights and field reality. Here's our lab study showing release from three shell thicknesses, 80, 200, and 380 nanometers. Clean curves, predictable behavior, clear differences. We applied CS to microscope slides, dried under ambient conditions, and measured AI release over time. This gives useful insights. Thicker shells, clearly slow release rates. But what does this mean for field performance? These beautiful lab curves are very far from field reality. In the field, you are not dealing with a microscope slide in a climate-controlled room. You have temperature swings, UV radiation, rain, dew cycles, and complex plant-surface interactions all happening simultaneously. The controlled environment that makes our measurements possible is exactly what makes them poor predictors of actual performance. This data helps us understand shell chemistry, but field release remains largely unpredictable, driven by weather and microenvironmental factors changing minute by minute. CS formulations today: marketed strengths versus practical weaknesses. Time to replace outdated paradigm. This slide captures the dual reality of CS formulations. On the surface, they present certain marketed strengths, but in practice, they suffer from significant weaknesses that make their current paradigm outdated. Strengths. First, CS formulations are promoted as reducing operator exposure, lowering potential hazards for human during handling. Second, they allow companies to position this product as different from standard ECs, SCs, or other formulations of the same active ingredient. This differentiation has value in marketing and regulatory narratives. Third, the slow release claim has strong commercial appeal, even if the reality doesn't match the promise. Weaknesses. Strong encapsulation often means reduced efficacy in the field, requiring higher doses, which undermines the value proposition. Weak encapsulation creates the opposite problem. A large fraction of the eye remains outside the capsule. This compromises storage stability, increases operator risk, and prevents co-formulation with incompatible actives. Another key issue is the unpredictability of release. CS formulations make active ingredients available in a way that is often out of sync with real pest or disease pressure. This mismatch means protection is not delivered when the crop needs it. And finally, there is the environmental dimension. Polyurea shells are not biodegradable and fall directly under the new microplastics regulations, creating regulatory pressure. Just we will talk about it. So, while CS formulations are still perceived as innovative, in reality, their weaknesses, agronomic, technological, and regulatory, outweigh their marketed strengths. Microplastics, the regulatory constraint. This is the regulatory reality we are facing in Europe, and it changes everything. EU Regulation 2023-2055 directly targets intentionally added microplastics in products, and our polymeric capsule shells in CS formulations are squarely in scope. The timeline is non-negotiable. Transition period ends October 17, 2031. After that date, you must either use compliant shell chemistry or prove exclusion from the regulation. Non-compliance means no EU market access. It's that simple. This isn't just a European issue to watch from afar. The EU often sets global regulatory trends, and their market size makes compliance essential for any major agrochemical company. Let's be specific about what we are dealing with. The regulation defines prohibited microplastics using four key criteria. First, synthetic or chemically modified polymer microparticles. Our synthetic polymer shells clearly fall here. Second, water insoluble and very slowly degradable, exactly what we have been engineering for stability. Third, size range, zero point 0.1 micrometers to 5 millimeters. CS capsules at 1 to 10 microns are right in the target zone. Finally, present at 0.01% by weight or higher and ingestible by organisms. CS shell loading easily exceeds this threshold. But here's the good news. There are clear exclusion paths. Shells that are biodegradable according to OECD tests, water-soluble above 2 grams per liter, natural unmodified polymers, or carbon-free systems can all qualify for exemption. During the transition period until 2031, we are not sitting idle. There are immediate requirements providing use and disposal instructions, annual release reporting to ECHA, and likely label updates. But the real strategic work is treating this regulation as a design constraint from day one. Don't wait until 2030 to start thinking about compliance. Choose shell chemistry now that meets the biodegradability criteria. Build your evidence package during formulation scale-up. The regulatory approval process will require solid documentation of biodegradation, and that data take time to generate properly. This is fundamentally reshaping how we design shells. Sustainability is no longer an add-on, but a core requirement. The US presents a different picture. At the federal level, EPA is focused on strategy and research, not restrictions. Under FIFRA, microencapsulation is still allowed with attention on pollinator risk rather than microplastics per se. But watch the states. California is defining microplastics and implementing monitoring programs. Alaska, Michigan, and Rhode Island are proposing product-specific bans. The patchwork of state regulations could become more challenging than a single federal standard. Summarizing U.S. operations, no national restrictions on CS capsules currently, but maintain strong label and pollinator risk management. Keep monitoring state actions, especially California, which often drives national trends. For global companies, the practical reality is that EU compliance will likely drive worldwide formulation strategies regardless of other regional requirements. Understanding controlled release fertilizers, CRF. Before diving into our CS future, let's understand why so many formulators look to controlled release fertilizers as a reference point. CRFs face the same microplastic regulations that apply to our capsule suspensions, making them valuable analog for both technical innovation and regulatory compliance. Many CRFs on the market today are polyurethane-coated granules, urea, MAP, potassium nitrate, NPK blends. Polymer coating technology shares similarities with our capsule chemistry, which is why CRFs offer instructive lessons. But here's the key point. While CRFs provide useful technical insights, we need to understand their fundamental differences from CS systems. The analogy has limits, and treating CS as simply a slow-release system with CRF logic won't solve our agronomic challenges. The market's benchmark case, polyurethane coating process. Using polyurethane-coated fertilizers as an example, let's see how polymer-coated CRF granules are made. The process involves pre-warming granules to 40-60 degrees and coating them in rotating drums or fluidized beds using two reactive streams. The chemistry centers on urethane formation through the reaction of isocyanates with polyols, forming urethane linkages that create the polymer backbone. The prepolymer route is common in CRF production. You form an NCO-terminated polyurethane prepolymer with excess diisocyanate, spray it onto granules, then chain extend and cross-link it on the granule surface. This layer-by-layer curing builds defect-free polymer shells. Coating levels vary significantly. Urea typically needs only 2 to 8% by weight, while NPK granules require 8 to 15% coating to achieve equivalent performance. The granule chemistry affects how much polymer protection you need. Nutrient release mechanism. CRFs stand out for their consistent diffusion-driven release. Water permeates the coating, dissolves the fertilizer salts, and forms a saturated brine inside. Osmotic pressure then drives nutrient diffusion outwards through the polymer film. The release rate is controlled by film thickness, permeability, NCO to OH ratio, polyol type, secondary reactions, and environmental factors like humidity and temperature. But the key difference from CS systems is that this process is predictable and modelable. The electrical conductivity curves you see demonstrate this predictability. We can measure electrical conductivity as a proxy for nutrient release and develop reliable models for different temperature conditions. This allows agronomic planning that aligns CRF timing with crop phenological stages. The 2N release profiles shown illustrate something beautiful. Temperature affects both release rates and plant development in parallel gradients. As temperature rises, CRF release accelerates, but so does plant growth and nutrient demand. This natural synchronization makes the controlled release concept workable for CRFs. The fertilizer release rate matches field demand through the same environmental driver that controls plant metabolism. CF and CRF, diverging paths in controlled release. Now we get to the heart of the matter, and this is really the crux of our discussion today. We need to understand why controlled release fertilizer strategies simply don't translate directly into crop protection systems. Let me walk you through the fundamental differences that explain why we can't just copy-paste solutions from one field to another. Structure. CRFs use millimeter-scale granules with micrometer-thick polymer shells. Our CS systems use micron-scale capsules with nanometer-thin shells. Physics are completely different. Contents. CRFs contain water-soluble salts that readily dissolve and diffuse. We are dealing with water-insoluble organic active ingredients that don't behave like fertilizer salts. Release mechanisms. CRF release is diffusion-driven and predictable. The CS release is variable, weather-dependent, and governed by multiple simultaneous mechanisms. And here's the crucial agronomic difference. Crop nutrition needs align with plant phenology. You can schedule when plants need nitrogen. But pest and disease pressure is episodic and weather dependent. You can't pre-schedule when aphids will attack or when fungal spores will germinate. So you need to make active ingredient available in the field just after the application of the formulation. When AI release is uncontrolled and slow, less AI is available when needed, so field efficacy declines. The shared challenge is microplastics regulation, but our solutions must diverge. CRS should continue evolving within the controlled release paradigm. CS formulations need a completely new approach. We must define new targets and performance metrics that acknowledge our economic reality rather than trying to force-feed the CRF model. This recognition is the foundation for developing the next generation of CS products that will succeed after 2031. CS, realigning release, demand, and degradation. On this slide, we are looking at how to realign the three core factors of CS formulations: release, crop demand, and biodegradation. Let's start with fertilizers. In controlled release fertilizers, the system works beautifully. Hot and humid weather speeds up diffusion through the coating, and at exactly the same time the crop's demand rises. Physics and biology move together. Now compare that with conventional CS. The whole concept is built on a diffusion-release model. But in the real field, the environment shuffles the cards. Sunlight, rain, humidity, drying all interfere with that need slow diffusion. And the result is unpredictable release. And it is always out of sync with crop demand. Release is not just diffusion driven. It's shuffled by the environment and ends up missing the crop's protection window. That's why in crop protection we need something different. Here, immediate availability of the active ingredient is essential. Efficacy must be achieved within minutes to hours. CS formulations must therefore be designed to trigger instant release right on spray. For example, through shell cracking, under UV sunlight, or thin film drying, while still staying stable in aqueous storage. And here's the opportunity. Those same triggers that open the shell, UV heat drying, can also drive biodegradation if we design the shell with photo and thermolabile linkages. This is the shift from diffusion-led release to environment-triggered release with co-triggered biodegradation. That realigns release and degradation with field demand. It gives us shells that no longer leave behind microplastics, but still deliver immediate bioavailability when it's needed most. So the new paradigm is simple. Release, demand, and degradation finally working together instead of against each other. Future CS paradigm. Where do we go from here? The path forward rests on three cornerstones that will define the next generation of CS formulations. First, speed. Immediate bioavailability that matches crop vulnerability windows. When pest pressure hits, the active ingredient must be there at once. Second, sustainability. Biodegradable shells must be built for regulatory compliance from day one, not added as an afterthought. Third, stability and compatibility. Shells must remain intact for 2-3 years on the shelf, yet perform instantly in the field. That includes tank mix reliability with hard water, AG1s, and other crop protection products. Farmers cannot accept products that restrict spray flexibility. And as we look ahead, we must not lose the core strengths that made CS technology valuable. Safer handling for operators, reduced dermal and inhalation exposure, and the ability to co-formulate otherwise incompatible active ingredients. These advantages must be preserved as we evolve. Let me stress something non-negotiable. Maintaining 2-3 years of shelf life stability. We need dense, well-cured shells that keep free AI below 1% at manufacture with minimal drift during storage. Here's the key point. Stability and compliance are not an either-or choice. Both must be achieved simultaneously through smart polymer design. This is where innovation truly happens, engineering polymers that remain stable for years in storage yet respond instantly to environmental triggers in the field. This is molecular level design that bridges regulation, polymer chemistry, and farmer needs. The goal is not only compliance, but a new generation of CS products, faster, safer, and more sustainable for both agriculture and the environment. We are at a fascinating crossroads where regulatory constraints are driving innovation in ways we could not have imagined 5 years ago. The microplastics challenge isn't just a hurdle, it's an opportunity to develop better, more sustainable formulation technologies. The future of CS formulations lies in smart polymer chemistry that satisfies both agronomic performance and environmental stewardship. We have the tools and knowledge to get there. It's about applying them strategically. Thank you for your attention.